derivative, and I will refresh your memory. This is the definition of the derivative. F prime of A, that is the derivative at a particular point A, is this thing. Lim h goes to 0, f of A plus h minus f of A divided by h. You definitely should have this memorized by the time we have our next quiz, I suppose. Could be on the quiz. Certainly on our next test. And I mentioned last time that if you took a calculus class in high school, you probably learned some kind of awesome trick, which is like 1,000,000 times easier than using this formula here. We eventually are going to get there, but for the purposes of this next assignment, you should be using this formula to find the derivatives, all right? And on our quizzes or tests or something, when I want you to do it this way, I will specifically say, use the definition of the derivative. That's this formula with the limit, all right? Eventually, like next week, maybe the end of this week, we're gonna talk about the awesome tricks, which will save you a lot of effort. But for now, I want us to put in the effort, all right? Any questions about that one? Great. Let's talk about some examples. Mostly today, I just want to do a bunch of examples of finding the derivative of various things, all right? I thought we'd start off with a little word problem. Here's a nice, cute little word problem. Let's say this is actually not made up. Most of my word problems are made up, but this is real life here. This is about a falling object that sort of accelerates as it falls. The distance traveled by a falling object is given by this formula. S of t equals 4.9 t squared. This is a true story. That 4.9 is a number which is based on the gravitational constant of the Earth, which has to do with how heavy the Earth is, how massive the Earth is. Anyway, this is the formula for the distance traveled by a falling object near the Earth, where t is in seconds, and the distance, s of t, is in meters, right? This is the true formula. Let's try, I got two questions, so the A part and the B part. The A part is, if I drop a rock, say, this of course does not account for anything like air resistance or that kind of thing. It's just in ideal conditions with no air in a vacuum. If I drop a rock, how fast is it moving after 5 seconds? Right? How fast is it moving after 5 seconds? Now, the formula there tells you how far it goes after 5 seconds. That's what the formula means. If I asked you how far has it gone after 5 seconds, you just plug t equals 5 into that formula there. But I asked you how fast is it moving. That means what I'm talking about here is not the distance, but it is the derivative of the distance, how fast the distance is changing. That's what how fast is it moving means. So my strategy is I will find the derivative first of all, and then use, I want the derivative at 5 seconds. So we'll find s prime of 5, right? This is what we need to find in this problem. That's because we know the derivative of the position is the velocity, right? It's how fast the position is changing, that's what velocity means, okay? S prime of 5. So to do that, we just use the formula, right? The formula that I wrote at the very beginning. You can see it at the top there. I'm going to use, instead of f, the function is called s, and instead of a, I use the number 5. You don't plug anything for h, because h is the variable that's in the limit there. So I'm going to say s prime of 5 is lim h goes to 0, s of 5 plus h minus s of 5 divided by h. All right, I plugged into the formula at the top there. I mean the formula for the derivative, which you can't see anymore, using a equals 5, and the function is called s. Sorry, my s's look a little bit like my 5s. Anyway, what do we do next? We should actually use the definition of S, and this is, you got to get used to this, but when it says S of 5 plus H, it means you go up here to this definition, and instead of T, you use 5 plus H. And you make sure you put the parentheses in the right places. Anyway, it's going to be 4.9. Instead of T, I messed it up. Instead of T, I use 5 plus H, like that. So 4.9 T squared, I plug in T equals 5 plus H. I get 4.9 times 5 plus H squared. All right, and then minus, that was only the first part there, minus S of 5. That means I go up to the function, I plug in 5. So that would be 4.9 times 5 squared. That's just a specific number. And then all of this over H. All right? That's the plugging in step. It's easy to mess it up right here in this step. And unfortunately, if you mess this step up, you're going to be screwed for the rest of it'll ruin your whole day. All right, let's continue. What can I do next? My goal is to try and simplify stuff, eventually take the limit by plugging in H equals 0, but you can't do that at the beginning or else you'll get 0 over 0. What should I do next? Let me shout it out. Yeah, what do you think? Yeah, do the FOIL thing with the 5 plus H. You need to expand that 5 plus H squared. So I will leave the 4.9 like it is, and then 5 plus H squared. When I multiply that, it's going to be 25 on the front. In the middle, I get 5h plus another 5h, which will be 10h. And on the end, I get h squared. And then minus 4.9 times, I don't want to get out my calculator. I'll just say 4.9 times 25, whatever that is. I'm not going to calculate it because I can see actually it's going to cancel in the next step. All right, let's distribute the 4.9. It's going to be 4.9 times 25, whatever that is, plus 4.9 times 10, I can do without a calculator. That's 49h, right? And then 4.9h squared. 4.9h squared minus 4.9 times 25 divided by h. All right? Keep on simplifying if you can. Eventually, you hope to cancel the h in the denominator, all right? Don't get too excited about it, though. Sometimes I see people say, oh, can I cancel the h like that? No, ma'am. You cannot cancel the h like that. When you cancel the h, you have to factor the h out of everything in the top. And the problem here is there isn't h in everything, like this guy here doesn't have an h on it. So anyway, don't prematurely try and cancel like that. What you got to do is, well, in this case, I can actually subtract those two numbers, right? 4.9 times 25, whatever that is. I have it. It's a positive, and then it's also a negative down there. So those guys go away. And now, there are no more constants in the numerator, and so I can factor h out of everything in the numerator. This seems like magic, but if you're doing things correctly, this will always happen, that all the constants in the numerator will cancel each other out. And if that doesn't happen, it means you messed it up, and you should try again. But anyway, I factor h out of everything. What remains is 49 plus 4.9h squared. And on the bottom, h, right? Yes?
Isn't it just 4.9h because you factored h out?
On the top, you mean? H, yeah, not h squared. Yeah, thank you. Yes. That is going to turn out to be irrelevant in the answer. Yeah, that's right. I might as well do it right. Okay, now can I cancel the h's? Yes, now you can cancel the h's because it is factored out of everything on the top. So we cancel the h's. What remains then is just 49. So then 49 plus 4.9h. All right, and now finally we take the limit by plugging in h equals 0. I end up with 49 plus 4.9 times 0, which is 0 there. So the answer is just 49. And the units on this would be meters per second. Because I said before the units were meters and seconds. All right? That sound reasonable? I don't know. Actually, this seems very fast to me, but this is a true story. If you drop something, 5 seconds later, it will be moving at 49 meters per second, which is quite fast. This is in the absence of any air resistance. All right. Any thoughts about that? I suppose 5 seconds is kind of a long time for something to fall, isn't it? Yeah. I'm not sure I've ever fallen for 5 seconds. Probably not. This is pretty fast to be falling. All right. Great. That was the part A. If I drop it, how fast is it moving after 5 seconds? Okay, the part B is kind of similar, I guess. I don't know. Here's the part B. How about this? If I drop it from a height of 3 meters, then how fast is it going when it hits the ground? Right? Very useful kinds of questions, I suppose. I mean, you wouldn't want to do this in your own life every day, but I'm sure you can imagine being able to answer these kinds of questions is pretty important in the real world for people who want to move things around. All right? If I drop something from a height of 3 meters, how fast is it going when it hits the ground? All right? To answer this, you need sort of two steps. First of all, how long did it take to hit the ground? And then we can answer how fast was it going after that duration. So my strategy here is first I'm going to find the time of impact. And then you find the derivative at that time. This is my strategy. Then find derivative at that time. All right? This is really the only sensible way to answer this question, and kind of in 2 parts like this. Okay, so first let's find the time that it hits the ground. Anyone like to suggest how we could do that? Remember, my master formula that I'm using here is the distance is 4.9 t squared, right? The distance after time t is 4.9 t squared. How could I find, really what I want to know is at what time does the distance become 3, right? How would we do that? Yeah.
Did you set the function equal to 0?
I liked it until you said the word 0. You want, this function is the total distance traveled. You wouldn't want to say the total distance traveled is 0. What do we want the distance traveled to be? 3. They're showing me the 3. Yeah, you want to know how long does it take to go 3 meters. So I'm going to set the distance equal to 3, and then solve for the time, right? This is how we solve this first preliminary question, find the time of impact. Set the distance equal to 3, and solve for t, all right? So this is not so hard, although you're going to have to use a calculator here. It's that, right? You set the distance equal to 3, and then you solve this for t. So I guess I would divide 4.9, 3 over 4.9, and then take the square root. T will be square root of 3 divided by 4.9. Without a calculator, this is as good as you can do. I plug this into my calculator. It's 0.782. Now, technically, sort of mathematically speaking, when you take that square root, really you should do a plus or minus, but in the context of this specific word problem, the plus is the one that makes sense. We're not considering negative time in this problem. All right? So this is the time we want. So my strategy in 2 parts, find the time of impact. This is it, right? And then find the derivative at that time. So now we're going to do s prime of this number, 0.782. This will give me the velocity at that time, which is the time at which the thing hits the ground. And this we're going to do, again, using the definition of the derivative. So I go s prime of 0.782. It is lim, h goes to 0, it's s of a plus h, where a is that weird number, 0.782 plus h minus s of 0.782 by h, right? And now we do basically the same business that we did in the part A, right? You just plug into the function here. S of 0.782 is going to be, sorry, I'm going to write my lim first. I hope you are being good little boys and girls and writing this lim every time. That is the main operation that we're doing. I know some people just don't like to write it because they got better things to do, I guess. I don't know. There seems to be a culture among math students. Some math students don't like to write anything. They're like, nah, I don't have to write that just because I don't want to. That's fine. It's a free country, but really your goal in writing these things down is to convince, I mean, let's be honest here. Your goal in writing these things down is to convince me that you know what you're doing. If you leave stuff out like that, you know, I won't mark it wrong, but you won't instill confidence in me. Anyway, what do we got? Plug in to S, right? This is going to be 4.9 times 0.782 plus h squared, and then minus 4.9 times 0.782, right? What? Squared, right? All of this divided by h. I hope you remember to write the over h every time, too. Some people don't even want to do that. They just keep rewriting little bits and pieces and then try and piece it all together at the end. You can do that if you want, but in my opinion, it's a lot easier if you just write it out clearly to begin with. Would you mind, just because I don't like dealing with these weird numbers, I'm going to factor 4.9 out of the numerator entirely. Both parts of the numerator here had a 4.9 on them. I just find it a little easier to factor that out. And then I'm going to do the FOIL. It's 0.782 squared. That's the front part. The middle part will be whatever 2 times 0.782 is. I did that before. It's 0.156 something or other, h, and then plus h squared. And then minus 0.782 squared divided by h. All right. I'm just trying to avoid having to use my calculator. What happens here? The constants, again, will cancel. This guy and this guy. 0.782 squared, that number is the same, occurring with a plus sign and then a minus sign, so they go away. And then I can factor h out of everything that remains. So it's going to be 4.9, that's just going to hang around till the end, I guess. H times 1.56 plus h divided by h. And these guys cancel out. And I finish by plugging in h equals 0. So finally, doing the limit, 4.9 times 1.56 plus 0. And my final answer is 4.9 times 1.56, which is that, 7.66. I did that on my calculator. And the units are meters per second. All right. I said you should write the lim every time. I don't really mean every time. I stopped writing it right here. And why did I stop writing it? It's because that is the point at which I actually did the lim operation, which is to plug in the h equals 0. All right. So you shouldn't just like blindly write it every time just because I said so. It is an operation, and you keep on writing it until you actually do the operation, which is in this step right here. That's why there's no lim. Your answer is just a number. You should not have the lim h goes to 0 of 7.66. That's the lim does not appear in your answer because that's an operation which you already did like 2 steps ago. So don't write the lim as part of the answer. All right? So if you drop something by 3 meters, this is how fast it will be moving when it hits the ground, 7.6 meters per second. All right? Anybody got any questions about that one? This is derivative in real life. Great. That is the end of that section in the book. I wanted to say, this is an announcement. I meant to say this at the beginning of class, but I forgot. Tomorrow evening is our first of the semester math colloquium. Colloquium means like a lecture or a talk or something. It's tomorrow evening, I believe at 5. I will give you more specific information tomorrow. I think it's 5 to 6. Actually, would you mind if I just look in my calendar here? It is 5 to 6. Yeah, it's going to be in the big room in the library. Like you go in the library and downstairs, I don't know what that's called, but the downstairs library. The math colloquium happens 3 or 4 times a semester, and usually we get some kind of outside speaker to come and give a talk about something interesting in the world of mathematics. Tomorrow is a special treat. It's going to be presented by some of our students who did a math research project over this past summer. And so 3 of our students, I think one of them is a senior and the other 2 are juniors this year, something like that. They're going to be talking about mathematical billiards. They did some research on a collection of math problems which involve things like a billiard ball bouncing around a weirdly shaped pool table or something like that. I don't know much about their research. I'm looking forward to hearing about it. So check it out. I was going to say something about FYE credit, but I'm not sure if you get FYE credit for this. The math colloquiums, if you are a math major, you are required to go to them when you're a senior, but you're not required to go to it now, but I would encourage anyone to check it out. I'm going to be there, but I won't wave to you and make a big deal. If you're with your friends, you want to play it cool, I will play it cool. Don't worry. All right, any questions about that? I will give you more information tomorrow about that. Okay, great. Let's go on to the next section in the book. It's called, come on, the derivative as a function. Thus far, we have been considering only the derivative at a specific point, which represents the slope of the curve at that point. And in the real world, it represents how fast the function is changing at that moment. But we can talk about the derivative. We can find the derivative without plugging in a specific point. Without plugging in a specific point. And then when you do plug in a specific point, the answer is just a number. If you don't plug in a specific point, but you leave the variable inside your function, you leave them as variables, then what you get at the end is another thing with leftover variables which have not yet been plugged in. So if you do this, you find the derivative without plugging in a specific point, we get a function as the answer. All right? If I were to plug in a number, I would get a number as the answer. But if I just leave the variables like they are without plugging them in, the thing that I end up with at the end will still have those variables in it, and it will be a function that we get at the end here. All right? And the definition of that, I'll just write the same thing again, but not considering any specific point, I'm just writing f prime of x instead of a, but it's going to look exactly the same. Is f of x plus h minus f of x divided by h. Sorry, with a limb. I left out the limb. All right? I'm a good boy, so I write the limb until I actually do the limb. Then I stop writing. All right, this is the definition of the derivative of a function. This is not plugging a specific point in, but you leave the variable x in there. All right? That's the only difference is I'm not using a specific point A. I am leaving the x's in there. So I will say, never plug in for x. You don't ever turn it into some number A. So x's remain in the answer, right? Eventually we do the limit, but that's plugging in for the h. So the h should not remain in the answer, but the x's do remain in the answer. In this way, we can think of the derivative kind of like an operation of itself, which takes a function, you do the derivative to it, and the answer is another function, all right? So in this way, the derivative is like a function transformation right? We start with a function, f of x. You do the derivative to it, and you obtain another function. Obtain another function, f prime of x, right? So the derivative as an operation is an operation of functions. You plug a function into it, and what comes out of it is another function, all right? And of course, the meaning of the other function, this f prime of x, its meaning, like in a real world problem, is this is measuring how fast f of x is changing. Right? The rate of change of f of x, that's what the derivative means. And the derivative is another function. If f of x is the first function, it changes over time. The derivative is another function which describes exactly how that first one was changing over time. All right? So let's try an example of this where I'm not going to plug a specific value into it. I'm just going to leave the derivative as a function. And then I got some for you guys to try. How about, this is a totally made up example. I wanted to make up a word problem here. Let's say my bank account balance changes over time. That's a true story. My bank account balance, I will just say, is given by this formula. F of t equals 2,000 plus 5 over t, where the units here, t is in days, and f of t is in dollars, right? This is my bank account balance from day to day. So on day 1, I guess my bank account balance is 2,000 plus 5 over 1, right? This is a made-up formula, but if you believe what I'm saying, on day 1 I have $2,005. On day 2 I have $2,002.50, something like that. All right. So let's find f prime of t. This is another function. What will this function mean? Can anyone describe, like in words, what's the meaning of this other function? The first function means how much money I have on day t. What would this other function mean? Yeah, what do you think? How much it's changing by? Yeah, right. So this means something like, there are a lot of ways you could say this. I would say something like how much my account changes on day t, right? It's different from f of t is how much money I actually have on day t. F prime of t would be something like how fast did my account balance change on that day. Could it increase? Could it decrease? Right? Okay, anyway, let's see if we can do it. So I begin with my definition of the derivative. It's this formula up here that I had before, right? My variable this time is t, but it's going to be lim, h goes to 0, f of t plus h minus f of t over h, right? I'm using t rather than x just because I use t in this problem, just for funsies. Okay, let's plug in the f's. That's how we begin such a problem. I go lim h goes to 0. All right, f of t plus h. My formula is up there, 2,000 plus 5 over t. So it's going to be 2,000 plus, how do I plug that one in? Yeah, what do you think? 5 over t plus h. Yeah, great. You go up to the original formula and you replace the t with a t plus h. So it becomes 2,000 plus 5 divided by t plus h. Great. And now, so that was just this part, f of t plus h. Now I go minus f of t. Minus is right there. F of t, I'll put it in parentheses, is just exactly what the formula says, as is, f of t, right? This is f of t, 2,000 plus 5 over t. And then all of this divided by h. Right? That's how we do it. And now, as in those other examples we did, we are going to try to recombine stuff, like simplify, do whatever, do the FOIL. Now, you don't do the FOIL in this one because there's no squaring, but you got to do something. Anyone have a suggestion? What can we do with this to simplify? I suppose the first step is not so hard, then it gets a little trickier. Yeah, that's a good start, and then it gets a little trickier, but yeah, for now, let's distribute the minus sign. It'll be minus 2,000 and then plus 5 over t. All of this divided by h. And we cancel the 2,000s, all right? This guy and this guy. So, and would you mind, I'm going to do a little something here. Just because what I see here is like fractions inside of fractions. I'm not into that fraction on fraction business. So to me, it's easier to express this. What I have here is these guys in the numerator are being divided by h. And to me, it's a lot easier to write that. Do you have another way to write it? Did I mess it up? Yeah, I think so. Yeah, thank you for that. This should have been a plus. This should have been a plus here, right here. I messed that up. And then that means this will be a minus. Thank you. He's right. All right. What I was saying is I want to avoid having fractions inside of fractions. My way to sort of clean that up a little bit is I have this business up here all divided by h. Rather than divided by h, I'm going to write it as a times 1 over h. I'm going to write 1 over h times that other stuff, which is 5 over t plus h minus 5 over t. All right. This is just to clean up the fraction inside of a fraction, which is always a little confusing to me. It's all divided by h, which is the same as all times 1 over h. All right. Anyway, what do we do now? Yeah, this is a little tricky, but the way to simplify this one is right here. We have to actually subtract the fractions. And the only way to do that is to make a common denominator in this subtraction here. Remember how to make a common denominator? You have to multiply each fraction by something to make their denominators the same. Do you have an idea what are you going to use for the common denominator? Yeah. Yeah, this is like one of those settings where the numbers are weird and you don't know what the common denominator is supposed to be. You can always just use the product of the two things as your denominator, and that's what we're going to do here. So I have this business is going to stay like it is. Okay, and now I'm going to multiply this one by t over t, because my common denominator is going to be t times t plus h. Right? This is how you make the common denominator. You have to multiply the top and the bottom by the same thing. And now let's see if we can work this out. 1 over h. Okay, so the first one is going to be up top 5t over t times t plus h. And the second one is going to be 5t plus 5h, I distributed there, over t times t plus h. Right? And now they have the same denominators. T times t plus h is the common denominator. We're almost done here. We're getting somewhere at least. Next, I can actually subtract the two fractions. Remember, once you have the common denominator, you leave the denominator the same, and then you subtract the numerator. So, I go, still got my 1 over h out here. Leave the denominator like it is, t times t plus h. And in the numerator, we subtract 5t minus, I'll write it out. Make sure you remember these parentheses, like so. All right? And now up top, the 5t's will cancel, and I will have a negative 5h left over. It's negative because I distribute the minus sign. 1 over h times negative 5h over t times t plus h. Almost done here. What can we do next? Yeah. Cancel the h's. Finally, this 1 over h, which was sitting out front, can cancel that h up there. And now we are ready to actually do the limit. So this, just writing, I'll write that. Finally, negative 5 over t times t plus h, right? Plug in h equals 0. I get minus 5 over t squared. And that's the answer. It's quite a journey to get there. We made it eventually. Anybody got any questions about that one? Great. Minus 5 over t squared. Okay. So let me just summarize here. We started with this, right? 2000 plus 5 over t. F prime of t was minus 5 over t squared, right? This is what I meant by saying when you do the derivative, it transforms the function. We started with this function right here. After doing the derivative, you get this completely different function right here. Now, I said completely different. Actually, there are sort of patterns about what happens to the function when you do this. And this is what the awesome tricks that I mentioned before are based on. And we'll talk about that eventually. I want to get into it right now, though. Let me just to remind us sort of what this means. F of 1 equals 2005. If you plug t equals 1 to that first one, what that means is, this means on day 1, I have this much money, $2,005, right? Whereas f prime of 1, if I plug t equals 1 into this formula, f prime of 1 is minus 5. And what that means is that is a measurement of how my account money is changing on day 1. So technically it means at the very beginning of day 1. So this one means on day 1, to be specific, I'm losing $5 per day, right? That's what the minus 5 there means. So technically it means at the moment of the beginning of day 1, like at time t is exactly 1, at that moment, I'm losing money at a rate of $5 per day, right? That's what these things mean. Any questions about that? All right, I want you guys to try out some derivatives on your own, see how it goes. So these are not as taxing as the one that I just did. So for each one, find f prime of x. And I just have 2 here, and they're both polynomials. 5 plus 2x minus x squared. And second one, 3 minus 7x. Maybe the second one's easier. I don't know. You can do them out of order if you want to. All right. See what you think. These ones are kind of standard examples. After that, I just want to do 2 more that are slightly harder. And then I think we'll be done with these simple derivative examples. Here, I'll give you the answers in case you want to check your answers. If you know the 6 tricks, the answer here should be 2 minus 2x, and the answer here should be negative 7, just a number. See what you think. I'll give you a bit. Feel free to talk to your friends about it. Okay. I'll give you a few more minutes and then we'll talk about them. I gotta write my answers slowly. No spoilers. All right, maybe we can talk about these. I know not everybody's finished, and that's fine. Anyway, like I said before, I don't know if you believe me, the first step is often the hardest. You've got to plug in f of x plus h. That's this much, f of x plus h. It means you go to the original function here, you just write as is, but you replace every x. Instead of x, you use x plus h. So it's going to say 5 first, and then instead of plus 2x, it's plus 2 times x plus h. And then minus, instead of x squared, it's x plus h squared. All right? And then you go minus f of x, which is just the whole thing exactly as written, and then divided by h. And then we just got to do a lot of simplifying, which in this case is doing FOIL and then rearranging stuff and canceling things, which is kind of a pain, but it's not, I mean, it's easier than that common denominator stuff that we did a few minutes ago, I think. So let's see how I'm doing here. I did the FOIL, I also distributed the 2, and I also distributed the minus sign here. I would suggest that you put the parentheses in there. There's a lot of chances to mess this up, and often, you know, when I see people making mistakes, it's most often because they couldn't keep straight the parentheses. Okay, anyway, I continue. H goes to 0. All right, one last thing. I will distribute the minus sign in the middle there. So it's going to be 5 plus 2x plus 2h minus x squared minus 2xh minus h squared minus 5 minus 2x plus x squared. And if I've done it properly, everything up top will cancel except for stuff that has a h on it. This should always happen, and if it doesn't happen, it means you messed it up somehow. So I got the 5 here and a minus 5. I got a plus 2x and a minus 2x. 2h is fine, it has h's on it. Minus x squared and a plus x squared. And now everything else that remains has an h in it. So this is, lim h goes to 0. Come on now. 2h minus 2xh minus h squared, right? That's just what's left over after I cancel all that stuff. What should I do next? I know you guys did it already. What do you say? Factor and cancel the h, right? So this, I factor h out. What remains is 2 minus 2x minus h divided by h. I cancel the h's. And finally, I take the limit by actually plugging in h equals 0. I get 2 minus 2x minus 0. 2 minus 2x is the answer. All right? I hope you made it. Anybody got any questions? If you didn't make it, it's probably because either you didn't plug it in correctly at the very beginning, or you just messed up the algebra at some point in the middle. All right? Excellent. Let's try that other one. It's maybe a little easier, although it feels a little weirder because you get a number as the answer. The other one was f of x equals 3 minus 7x. So for my derivative, I begin by, I'll just write it out, f of x plus h minus f of x over h. This I will say again, you should have that formula memorized eventually by the time of our, I suppose, our next quiz. You should expect to do something like this. Oh, with the A's, not with the S. Oh, it's pretty much the same. Anyway, f of x plus h is 3 minus 7 x plus h, right? You go back to the formula, and you just plug in, instead of x, you use x plus h. And then I go minus f of x is just what it is, 3 minus 7x, all this divided by h. And now, as before, you distribute, rearrange stuff, hopefully cancel things out. What do I get? On the top, 3 minus 7x minus 7h minus 3 plus 7x divided by h. And then we cancel the 3's and the 7x's. And then we cancel the h. And all that's left over this time is just a number. It says minus 7h divided by h. The h's cancel. Get minus 7. That's the derivative. It's strange, usually we expect the derivative to be a function, that is, it has x's in it. This is a function, it's just a constant function. It happens to have no x in it, but that's sort of a coincidence. Sometimes when you take the derivative, the x can go away entirely. All right. Any questions about that? I hope that you got those guys, those folks. All right, great. Like I said, I have just 2 more examples that are a little bit harder than these ones we've been doing. I hope you don't mind. Some slightly harder ones. Harder, I meant to write harder. I wrote hoarder, that's also good. A little hoarder. I got 2 more. Okay, the first one is f of x equals square root of x. Let's see if we can do that. Find the derivative of square root of x. It's a little bit harder. F prime of x is going to be, well, I'll write the formula again. If you write it enough times, you will naturally memorize it. That's my experience, at least. I'm not really into asking people to memorize things in general, but some things are worth remembering. So, I begin with lim, h goes to 0. Anybody want to tell me what is it going to be when I do f of x plus h? What does that look like? Yeah. Square root of x plus h, all inside the square root, like that. That's my f of x plus h. And then I go minus f of x is square root x, and then divided by h, all right? And now we have to do this limit by simplifying somehow. Well, any suggestions? What should I do to simplify in this one? Yeah. Yeah, you do the rationalize trick, all right? You multiply the top and the bottom by, well, what's it going to be in this case? Yeah, it's that same thing you see in the numerator, but with a plus instead of a minus. This is the old rationalized trick, which you should expect to have to do this whenever you see a square root involved in your formula. All right? Okay, what happens when we do it? Well, it's still lim, h goes to 0. All right, the bottom just becomes h times that other stuff, and you could distribute the h if you want to, but it's actually better to leave it undistributed, because eventually you're going to cancel the h on the top and the bottom, and you're going to want it to be factored out when you do canceling. What about on the top? What we get, remember, when you have one of these rationalizing things, what you end up getting is just like the first part squared minus the second part squared. And in this case, those squarings will just kill the square root signs. So the first part squared will just give me an x plus h, minus the second part squared will just give me an x. So it's like that. This is not that much harder. You just got to remember to do the rationalizing trick. All right? And now we continue to, cancel things, simplify as much as we can. So here I can see the x's will cancel. I got an x and then a minus x. And then all that remains is just h, and that h will cancel with the h on the bottom. So this will be h divided by h times that thing, root x plus h plus root x, right? And now my h's will cancel. And all that remains is that stuff on the bottom, and that I can take the limit. So I'm going to get 1 over square root x plus 0 plus square root x, right? I just did the limit by plugging h equals 0. Of course, root x plus 0 is just root x. So really what I have on the bottom is root x plus root x. So just to simplify that, it's that. 1 over 2 root x. This is the derivative of the square root of x. It's 1 over 2 root x. Any questions about that one? That was a little bit harder than the others. I guess you just have to remember how to do that rationalizing trick. Okay, and then I got one more, which really, this one really is harder, in my opinion. This is, I would say, the most complicated one of these examples that we're going to try to do in this, long style derivative using the definition with the limit. X plus 3 over x minus 1. Let's see if we can find the derivative of this function. So it's going to be, as always, I'll start off with my lim. H goes to 0. F of x plus h minus f of x over h. Okay, let's do it. Anybody want to say what is f of x plus h going to look like? Everything's going to be over h. You want to tell me what is f of x plus h? What do you think? Excellent. You go to the original formula here, and you replace every x by x plus h. So it's x plus h plus 3, and x plus h minus 1 on the bottom. Great. Minus f of x, that means you just use the function just as is, x plus 3 over x minus 1. All right? And now, we have to continue simplifying here. This is where things get a little bit nasty in this one. What are we going to have to do here? Yeah, you got to make a common denominator. Like inside the numerator here, I have 2 fractions which I'm subtracting. You have to subtract those 2 fractions by making a common denominator. I'm going to, like I did in that other example, and I would encourage you to do this whenever convenient. Instead of everything divided by h, I'm going to make it a 1 over h in the front. And then what I have, I'm not doing this step just yet, but I'm going to multiply something in there to make a common denominator, right? This is times, it's going to be something over something to make my common denominator. And just like we experienced before, in order to make a common denominator here, since you don't have numbers, you can't sort of figure out the least common multiple. You just have to use the product of these 2 things. So the first one I'm going to multiply by x minus 1 over x minus 1. And the second one I'm going to multiply by that other denominator over itself, x plus h plus 3 over x plus h plus 3. All right? Any questions about that so far? Did I mess it up? Oh yeah. Yeah, sorry, it should be the denominators. I saw the faces seemed confused. It was my fault. Minus 1 here. Thank you. All right, great. Now, we got to actually multiply these things. This is a pain because we have this, trinomial, if I may use the fancy term. You got to actually distribute this thing, which is like doing the FOIL, but there's three parts to it. It's all right, we can handle it. 1 over h. Okay, my common denominator is going to be this, x plus h minus 1 times x minus 1. And just because I know how these things go, it's usually not helpful to try to expand the denominator, but we are going to have to multiply out the numerators. What do I get when I multiply these numerators here? My strategy is going to be, I'll go through this whole thing, multiplying each time by x, and then I go through this whole thing again, multiplying by -1. That's how you distribute this sort of trinomial over this x minus 1. So I go through the whole trinomial, multiply by x each time. I get x squared plus hx plus 3x. All right, and then I go plus, and now I go through and multiply by -1 each time. Minus x, minus h, minus 3. All right, that's the portion of the numerator you get from this guy. I hope that you got something like that. You go through and multiply each of those by x, and then also multiply each of those by -1. Okay, and then I see minus, I'm subtracting the second fraction from the first. And I do the same kind of super duper FOIL here. All right, it looks similar, but it's not exactly the same. So I take x plus 3 and multiply it across this. I'm going to multiply everything across by x first. It gives me x squared plus hx minus x. And then multiply everything by 3. 3x plus 3h minus 3, like so. This is as nasty as it's going to get. From now on, we're just going to simplify, and it'll get simpler every time. Any questions about that so far? This is a tricky bunch of simple algebra, I guess, but complicated just because of how much stuff is there. All right, what do I got? 1 over h, and now I'm going to distribute the minus sign, I guess. X squared plus hx plus 3x minus x minus h minus 3 minus x squared minus hx plus x minus 3x minus 3h plus 3. I hope I didn't mess any of that up. I just distributed the minus sign across the second half of that. And now it's time to cancel stuff out. Hopefully most of this stuff will cancel. I see x squared in the beginning and a minus x squared in the middle. Next I see hx. I think there's another hx here, right? Plus hx minus hx. Next, plus 3x, there's a minus 3x. Minus x, there's a plus x. Feeling good about this. Minus h, there's nothing to cancel that with. And then minus 3 and a plus 3, they cancel. So everything canceled except for minus h and minus 3h. So we're almost done here. All I get, what remains on the top? Anybody still with me here? Negative 4h, yeah. Thank you for staying on the journey. X plus h minus 1, x minus 1 on the bottom. All right, finally we cancel the h's. I have a 1 over h in the front, which will cancel that h on the top. And then we can take the limit by plugging in h going to 0. Finally, we get negative 4 on top, and on the bottom, x plus 0 minus 1, and then x minus 1. So I would say it's negative 4 over x minus 1 squared, if you like. All right. That was a long-winded one. We're not going to do, 5 more of those. This is about as taxing as these are going to be. So I wanted to do a hard one before you encounter this on the street. All right. Any questions about that one? Great. We got 10 more minutes. I think we can talk a little bit about what I want to talk about next. Sometimes the derivative of a function does not exist, and I just want to talk about that. This will be, less technical, more looking at pictures. The derivative is a limit of something, right? So the derivative is a limit of something. And so, because it's a limit, you should expect that sometimes the limit will not exist, right? Like that does happen sometimes in limits. So there are certain situations in which the derivative just will not exist. I could ask you to tell me the derivative, and the answer might be like dne, right? The derivative does not exist. Derivative is a limit of something, so it might not exist, right? And there are a few different reasons why this can happen. So actually the example that we just did is a situation in which the derivative fails to exist. I gotta refresh my memory. It was x plus 3 over x minus 1. And the derivative, eventually we worked it out, was 4 over x minus 1 squared. Right? And you will notice the derivative here, this one, does not exist if x equals 1, right? Because if I were to use x equal 1 in the denominator there, it would give me a 0 in the denominator. So the derivative does not exist at x equals 1 in this case. So the language for this, we say, like in this particular situation, we say that f itself is not differentiable at x equal 1. Not differentiable means the derivative does not exist. I said not equals 0. I mean does not exist. That's different. The derivative does not exist. All right? Differentiable is the word, it's like the adjective form of has a derivative. All right? The derivative does not exist at that particular point. Although in this example, specifically, it's not all that surprising because even in that case, in this example, also f of 1 does not exist, right? Like the function itself doesn't even exist when x equal 1. And so maybe it's not a surprise that also the derivative does not exist at that point. It's because this function has a vertical asymptote at x equal 1. And since there's no value at x equal 1, also like there's no slope at x equal 1 because there just isn't any value at all at that point. This is one way in which a function can fail to have a derivative, just like if the function doesn't even exist at that point at all, then it doesn't have a derivative at that point either. But there are other ways that the function can be non-differentiable. So I will say, let me just say first of all, when f of, say, some specific point A does not exist, sorry, this is sloppy handwriting. If you have a certain value where the function doesn't even exist, when f of A does not exist, then certainly f prime of A also does not exist. But sometimes it is possible for the original function to exist, but still the derivative does not exist, for reasons that, like, somehow, for some reason, the slope doesn't exist, even though the original function does exist. So I will say, but sometimes f prime does not exist, even when f of A does exist. And there's actually kind of two different scenarios that you can identify by looking at a graph in which this can happen. So one scenario I'm going to call a pointy point, and the other I will call a vertical slope. So a pointy point, what I mean by that on a graph is something like this. Oh, not what I wanted. Where the graph actually has like a sharp point in it. Yeah? Oh, you want to use some fancy words? Yeah, this is sometimes called a cusp. So technically a cusp means that the two curves which go into this point are tangent to one another, which is what the picture I drew there looks like, but by pointy point, it could also be just something maybe like that. This is not a cusp, technically, but yeah, that's a fancier word for it. I'm sure you can imagine that pointy point is not really the technical term for this. But when the curve has a sharp point in it. The derivative at that point does not exist. Why not? Because this right here has no specific tangent line, right? Remember, the derivative is meant to measure the slope of the tangent line, and the tangent line is supposed to be a line which is like the unique line which goes through that point only, but otherwise doesn't touch the curve nearby. But in this case, actually, there are many possible candidates for the tangent line. Like this looks like a tangent line, but also that or that. All of these lines go through the point and don't touch the curve at any other nearby points. But they all have different slopes. So in an example like this with a pointy point, there is no one specific slope of the tangent line, and that's why the derivative doesn't exist at such a point. The other way that the derivative could fail to exist is with a vertical slope. So it is possible to have a function which does something like this, where the slope actually becomes straight up vertical at a point. All right, and in this case, the derivative does not exist at that point, but it's for different reasons than what I said before. Because here, actually, there still is one tangent line. It just happens to be a vertical line. All right? But remember, the derivative is supposed to be the slope of the tangent line. In this case, the tangent line is vertical. So what would the slope of that tangent line be? The answer is it doesn't have a slope. A vertical line doesn't have a slope because you can't do the rise over run because there's no run. Like any rise over run in that case would have a division, something divided by 0. So this right here, the derivative does not exist because the slope does not exist of a vertical line. You might say it's like infinite slope, right? You could say that. But in any case, the derivative does not exist because the derivative is supposed to be a number. It's not supposed to be infinity, right? And you can't. It's really a problem of dividing by 0, which is very different from the issue on the side here. Can I tell you a little interesting fact about dividing by 0 that I saw the other day? Actually, this is like a few weeks ago. I was driving on the Merritt Parkway, and a Tesla drove past me going really fast. And the Tesla license plate was this. MPG0. This, I assume, means miles per gallon, because it's an electric car, right? I saw that. I thought, all right, I know what this guy means. He's in an electric car. But you can tell, I've been thinking about this ever since. This is a few weeks ago. An electric car doesn't get 0 miles per gallon, right? Right? But, like, my car gets, 30 miles per gallon. That's better than 0, isn't it? Really, an electric car, miles per gallon, is like, the Tesla is like a 0 down here, right? You should have said MPG infinity or MPG DNE, right? Like I'm concerned about this gentleman. He paid good money for that car and the fancy license plate. Mathematically inaccurate. All right, see you all tomorrow. See you.
Thank you.